Hello everyone, welcome back to my channel. Today I'm going to talk about the direct stiffness analysis method for 2D truss structure, and this is the example that we're going to solve. And as you know, the truss structure only has the axial force, so that is what we're going to find. Okay, before I start, I want you to click the subscribe and hit the notification button so you won't miss the new video I will upload every week. And after you watch this video, if you like it, please put the thumb up as well. Alright, for our problem, we have the module of elasticity equal to 10 power by 4 ksi. The area of each bar equal to 0.111 square inches, and for the array in the Python, the index will start from 0, so the degree of freedom will also start from 0. So as you know, the first node should be node number 0, and then 1, 2 until the node 7, and the degree of freedom at each node will start from 0, 1, 2, 3 until 14 to 15. Okay, so I will start writing a small program in Python, and this is the IDE that I'm going to use. I will use the spider. It's a good program for Python. So the first thing, I will import the library first. The important library that I'm going to use will be the NumPy and the Matlab for plot the structure, the deformed structure. So first I will import the NumPy, and next one is the Matlab library. Okay, next I will import the data of the truss. For example, like the coordinate of each node, the property of each bar. So first I will start with import truss fracture data. And first one, E is the Young modulus, or modulus of elasticity, and the cross sectional area. And next I will create an array, node and bar. So the first array node will contain the location of each node. So we start from the node number 0, and the coordinate will be x equal to 0 and y equal to 100 inches. So I will use the command append. So it's going to be like this. And for node number 1 will be the input the same way. So this will be 120 and 120. you will need to import the data like this until the last node of this structure. So I'm going to skip this part to make this video as short as possible. Okay, for the next array, the array bars, it will contain the information that the bar associated with. So the information is the node numbers. For example, bar number 1, it will start from node 0 to node number 1. And bar number 2 will start from node number 1 to node number 2. Okay, so I will input the information here. So this is the first bar. It will start from node number 0 and to node number 1. And for bar number 2, we start from node number 1 to node number 2. Okay, now every bar information is collected. Next, I need to convert this array to the NumPy array. So I'm going to use the command from the NumPy library. Okay, so the next information that we need to import is the load. So the load is applied to the node number 7, because the Python array start from 0, so this will be node number 7, and it will be at the axis Y. So I'm going to write this apply force, and I will call this with the P, and I will create an array this command will create an array, and each items in the array equal to 0, and the size of the array will follow the size of the array nodes. Okay, so now I will apply the force by import the information 7.1. So this 7 means that it is the force applied to node 7, and 1 is the y-axis. So we have 0, 0 or 1 if the force applied to the x-axis. This will equal to 0. But in this case it applied to the y-axis, so this one will be equal to 1. So I will import the number here. The number will be negative because the direction of the force different or opposite to the direction of the degree of freedom. Okay, the next part is the support displacement. I will call this UR, and we have two support, node number 0 and node number 4, and these two are the pin support. So the deformation, the placement at the node number 0 and number 4 will be equal to 0 at both axes x and y. So we go into import 4 number here. So this 2 is for node number 0, and this will be for node number 4. Okay, the next part is the condition for the degree of freedom. So I'm going to call the array DOF_CON. It stands for degree of freedom condition. I'm going to create the numpy array. Okay, this array will have the item, all the item equal to 1, and the size will follow the size of the array nodes. And this command here will apply to all the item in the array. The item will be the integer data, and the 1 here will equal to free degree of freedom. So at the degree of freedom 0 and 1, 8 and 9 will be equal to are not equal to 1, because it is the support degree of freedom. It is not the free degree of freedom. So we're going to define the condition at the 0 and a column equal to 0. So I'm going to write here 1 equal to free and 0 equal to fixed. So this means that the value 0 will apply to the node number 0 and both axes x and y, because both degree of freedom 0 and 1 will be fixed. And for the other support, it will be at the node number 4. So I'm going to import here 4. So this is the condition for the degree of freedom. Now I will start the structural analysis. So I will input new part. So we call this Truss structural analysis. I will create a function we call Truss analysis. Okay, so the first thing I will create a variable. So this is the number of the node. and NE is the number of elements. So we're going to use the command line on the array bars. And next one is number degree of freedom, because this is the 2D truss, so the degree of freedom at each node will be equal to 2. And next one is the total number of degree of freedom, so it will be equal to DOF multiplied by number of node. Now we got of all this information, we can start using the direct stiffness analysis method to do the structural analysis of this truss structure. For those who don't know the direct stiffness method, you can watch my previous video. I will leave the link in the description. First, I will find the transformation vector. So I'm going to start the next part. I will call this structural analysis, and to form the transformation vector you need the cos alpha, sin alpha, and so you need the information or the increment of the axis x and y of each member. So I'm going to do the subtraction. So the first part here, it will take the information from the end point of the bar and subtract the value from the start point of the bar. So the value of the bar will start from the first bar to the last bar. So we need to import the column here, and the value 1 represent the second column of the second item of the bar array, and the column here will take the the x and y axis from the node. So okay, for in order to easy to understand, I will talk in example. So let's say if I take the bar number 3 here. So the first part will take the information from node number 3 and multiply by subtract by the information from node number 2. So the value here will be the bar number for the bar number 3. In this case it will be value 2, because the Python will start from 0. So this will be 0, 1 and 2, and this is the bar number 2. So the value 1 here will take the node 3, and this is 0, it will be equal to 2. So it will equal to something like this. because the value here will be equal to 3 here, and this will be 2. And for this value, we will take from each column. So the node number 3 will be this one, because we will start from 0, 1, 2, and 3, and it will take the x and y axis and subtract with the node number 2, this one, and the x axis will subtract the x axis, and y axis will subtract the y axis. So this is the value d. And the next one, we going to define the cosine and sine alpha. So I will name this angle and use the information from array d and divide by the L. L is the length of each bar, so we're going to define the L. Now you can use the formula square and d power by 2, and you need to do the summation. Okay, so this is the length of each bar. Now to subtract this array by this array, you need to transpose the vector d. So I'm going to use the command .t here. It means that this will be the exposed matrix of the d. Okay, now I can show you the result by using the command print. Okay, I need to run the function. Okay, so this is the angle matrix. Now this is not the correct one, because the transformation vector will contain minus cosine alpha, minus sine alpha, cosine alpha, and minus and sine alpha. So we need the value negative, negative, and then a positive and positive. But we already have the cosine and sine, so we need to define the negative value. Now I will use okay, I will call this A. A will be a transformation vector. I will use the command concatenate and import the value from array angle. Okay, now we'll print the transformation vector. So this is the result of transformation vector. So it looks something like this, as you can see here. So this is the minus cosine alpha, minus sine alpha, cosine alpha, and sine alpha for each bar. So this matrix will be the 15 by 4. Okay, now we got the transformation vector. The next we can do is form the structural stiffness. And if you watch my previous video, you will know how to form the global stiffness. So we start from the local stiffness of each member and then form the global stiffness. And this is the information that we need to use. We have the transformation vector and length and EA, Young modulus, and the cross-sectional area. Okay, so I will call this K. K is the global stiffness matrix, and the size will be total number of degree of freedom by total number of degree of freedom. So to form this matrix, I will need to run a loop for each member. So the K will start from 0 to the rank of the number of elements. So in this case we start from 0 to 14. Okay, so the first thing is we need to define the degree of freedom. Now if you look at the node here, it starts from 0 to 7, and for the 0 the degree of freedom will be 0, 1, and for the node number 1 it will be 2 and 3. So based on this information we can define the degree of freedom for each node. So I'm going to create a variable. So it will take the information from the bar array. So for example, if K is equal to 0, this bar will be the bar 0. So we will take the information from here, and the bar start from node number 0 to node number 1. So the value here will be 2 multiplied by 0 and 2 multiplied by 1. So that value will be the degree of freedom, 0 and then 1, but this multiplied by 2, so the last one will be equal to 2. So we need to modify it a little bit. So I'm going to call the degree of freedom, in this case will be the index array, and I will use the command or underscore Okay, so this is the degree of freedom. I will show you the result from this line. Okay, I will change this to 1. I will show you the result from the bar number 0. So this is 1 2 0 1 and 2 3. So now you can see that the bar number 0 start from 0 1 and 2 3. So this is what the this line do. It will create the degree of freedom at each node. So now we got the degree of freedom. We can form the global stiffness. Now before we form the global stiffness, as you know here, you need to know the local stiffness first. And to find the local stiffness, you can use this formula. So now I will call this ES. It is the stiffness for each element. So what we need to do is do the dot product of the vector A and A here. So the first one will be the vector A transpose, but we need to create a new axis. And we need to multiply by E and A, and for the last one is the transformation vector, so A, and for each element, so this will be K, and again a new axis, and divided by length of each element. So again, I can show you the result here. So this is the local stiffness for element 0. Now we can use the information from each local stiffness to form the global stiffness. So the big K here will form by the index, the value index here. So in order to use this, I'm going to need a command ix, and we going to use the data from the index array. Okay, this means that we take the data from the index, from the degree of freedom, the row value and the column value, and do the summation for each local stiffness. For example, here you can look at the node here. If I want to find the value K11 here, I need the value K11 from each local stiffness. So this will take the value K11 here and K11 here to do the summation, and we got the value K11 here, and it will apply to all the item in the global stiffness. So the command here will we'll take the index value applied to each row and each column, and do the summation for the each local stiffness. It's a little bit complicated, but I think if you understand the theory in my previous video, you will understand this code. Okay, now I will show you the result. Okay, because this is not correct, I will change this to NE again. Okay, so this is the global stiffness. Now we don't need to verify this. We will complete the code first, and then we verify the result to see if the result is correct or not. Okay, next part I will define which degree of freedom is the free degree of freedom, and which one is the support degree of freedom. So first I'm going to start with free degree of freedom. So we're going to need the information from the array DOF-CON that we define in the first part. So I'm going to flatten this array, and I will find the index of the value that not 0. So the free degree of freedom will take the index that the DOF-CON is not equal to 0. Now we show you the result. So this is the index that it's not equal to 0. So as you can see here, it starts from 2, 3, 4, 5, 6, 7, and then skip to 10, 11 to 15. So the value that the value it will not take, it is 0, 1, 8, and 9. So as you can see here, because we define this value equal to 0. Now for the support DOF, it's actually just the same method here, but we will modify it a little bit because the value for the support DOF is equal to 0. So I'm going to import this equal to 0, and okay, and add a bracket. Now I can show you the result again. So this is the support degree of freedom, 1, 0 and 8, 9. You can see here 0, 1 and 8, 9. Now after we got this information, we can divide the global stiffness into some part like this: KFF, KFO, KOF, and the last one KOO. So the first one is KFF. If we take the value from the array big K and the value it take you will take the free degree of freedom. So I'm going to put the index of the free degree of freedom. So this will form the matrix KFF. Okay, I will show you the result. So this is the matrix KFF. For the next part is KFR, and the command here will be the same, but we change this one to support DOF. And for the next one is KOF, it will be equal to KFR transpose. For the last part, KRR. Okay, sorry. Okay, we need to change this to support DOF. Okay, now I will print the KRR. So this is the last part of the matrix. So we will need this matrix in order to find the reaction force. Okay, now we got the global stiffness. We can find the deformation array. So before we do that, we will need to flatten the array P here. So I'm going to call this PF and use the command flatten. And we will select only the value from free degree of freedom. So I'm going to, so I need to import the index from the array free degree of freedom. Okay, next part is UF. UF is the result from the from this formula. So we need KFF, the inverse matrix of KFF, and do the product of these two matrices. So in the Python, we have a command here in order to solve for that value. Now we just need to input the matrix KFF and PF, and now we got the result UF. So I can print this result. So this is the deformation at each free degree of freedom. Now you can collect the data and form it into the matrix U. So the U will contain all the deformation data. Okay, now I will collect the data from the UF. So for the array U here, will take the value from UF, but it will take only at the 3 degree of freedom. And the next one we can collect from the support degree of freedom. But remember that UR is already equal to 0, so this will not do anything. But we just in case the UR is not equal to 0, so we need this line. Okay, for the next one, you will need to extract the data from the matrix U, and in order to find the axial force for each member. So you can see the vector U here. It is the deformation vector for each element. For example, for element number 1, and in this case it will call element 0. It will start from the degree of freedom 0, 1, 2, and 3. So the deformation vector will be U0, U1, U2, and U3. So that's what we need in order to find the axial force. But before we do that, I will reshape the array U. And I can print the result. So the array U will look like this. So this is the first degree of first node. We have degree of freedom 0 and 1. So the number of the row is the number of the node, and number of the column is the number of degree of freedom. And we need the small u. Now we use the command concatenate again. So in order to find the degree of freedom for each bar, we will need the information from this array. Okay, you can see here the bar will start from 0 to 14, and the value 0, it is the x-axis, and 1 is the y-axis, and the command axis equal to 1 here. It will take the value in the horizontal direction. Okay, maybe I can print the result. let's say you want to know the deformation for bar number 0. So this will start from 0, 0 and this value. So the first 0, 2, 0 because it is at the pin support, and the last value it's equal to some number here because the node number 1 will deform because this is the free node. So we got the small u, and now we can find the axial force. So for the axial force array, I will call this n, and we use the formula EA divided by L, and we will need the transformation vector again, and then the last one is vector u. So multiply by the transformation vector and u, and because we need to do the dot product of these two vector, so we need to sum the do the summation for each value after the multiplication. Okay, this is the result of the structural analysis. For the next one, we need to find the reaction force, so we call this R. And for the formula, if we take the value KRF multiplied by UF and plus the KRR multiplied by UR. Okay, again we need to do the summation. I think something wrong here. Okay, this is the big U. Okay, now for the last part, I will reshape the array R to row and DOF column. So the two row here, because we have only two support, so I put the number 2 here. Now we can return the result. So the result that we need is the array N, and then the array R, and the last one is the deformation array. So now we got the result. Okay, I will create another part and call this result. So the first thing I need to find is N, and then R and U, and run this function. And next I can print the result. So the first one, let's call this axial force, and for positive positive value will be tension, and negative value will be compression. And next I will print the value n, and for the next result will be the reaction force. Positive will be upward and negative will be downward, and print all. The last one is the deformation value. Okay, now I can try and print the result. Okay, this may look a little bit messy, so I'm going to create a new axis and do the transpose of this vector. Okay, this is the result. So this is the axial force for the first bar, second bar, and third bar, and until the last bar. And this is the reaction force, and this is the deformation at each node. So this is the result that we want. And the next part, or the last part of this video, I will show you how to plot the structure. So in order to do that, I will create another function. So I'm going to call this plot, and I will need the node. For the node value here will be the value from this array, and the next one, let's call this C. C is color, LT, LW, and LG. You will know what this is in a moment. Now to plot, we will need to run a loop and plot 1 bar, 2 bar for each loop. So the I here in range of length of the array bars. And first I need the coordinate from each bar, so I will call this xi and f. So xi is the coordinate of the x-axis for the start point of a bar, and hf is the end point, the axis, x-axis of the end point. So I'm going to take the data from the array node and then bars. And the value hf, we change this to 1. So the value 0 and 0 here represent the x-axis, and 0 and 1 here is the first point and the last point of the bar, respectively. And it is the same for the y-axis, but we need to change this to 1 and 1. Now to plot the those lines, I will run a command from the library Matlab. So the first one is xi xf, and then yi and yf. For the color, if we equal to C, the input data here, and for the next one it is the line style. It equal to LT, and the last one is line width. It's equal to LW, and the last part of the plot here, I will create the label. So I will use the command set label. So the label here will will be shown in the legend form. So I'm going to turn on the command legend, and let's set a size here for the legend. I think this colon. Okay, now the function is complete. We can run this function. Okay, for the first plot here, I'm going to use the gray color and dash dash. The line width will equal to 1, and the legend of the first plot is undeformed. Okay, now I can run. So this is the undeformed bar. So as you can see here, this is the gray color. The line is dash dash, and width is 1. And it doesn't show the legend, so I'm going to fix something. Okay, this is not correct. Okay, this is the legend. Okay, I need to clear this. Now for the next part, I will plot the deform structure. So we need the value from the U array. So I'm going to call this deform nodes. So I name this D nodes, and it will do the it will equal to the summation of the array U and nodes. But you can do the scale also. So I'm going to call this scale, and first I will use the value 1 here, and again use this command, use this function, but this time we need this value, and I will change this to red, and the value here is 1, the same, but this will be the deform shape. So I'm going to name this deform, and you can run, I can run this. So this is the deform shape. I think I need to change this. Let's use the only one dash. This is mean that it is a straight line, and I think the scale here is already okay, so I'm not going to change this. I will keep it 1. So this is the result. Maybe I can change this to 2. Okay, so this is the result of the structural analysis. So as you can see here, we need only 110 lines in order to find the axial force and plot the result like this. Now in order to verify this result, I already do the structural analysis in the SAP 2000, so you can compare it. This is the first bar. It's the axial force is equal to 24.99, and you can see the result here, and you can check the result for this one. This will be 1 2 3 4. So 1 2 3 4, it's negative 25. So this is negative 25. Now you can also check the deformation. For example, this is the deformation at node number 2. You can check here. I think I show the deformed shape first. Deformation at node number 2, 2.7 and minus 4.22. So this is 2.7 and minus 4.22. So you can see the result are the same. Next one, you can show the reaction force. So this is the reaction force. For the first node is minus 30 and 5.0. This is the reaction force for the node number 1. So as you can see, the results are the same. So you can use this code now for finding the axial force for the 2D truss, and I can say that any 2D truss you can use this code to find the internal force. So this is the end of my video. I hope you guys can get the concept of this video and apply to your own project. So if you like this video, please put a thumb up and don't forget to subscribe and hit the notification button. Thank you for watching. I'll see you guys in my next video.